Algebra Unit 12, Lesson 5, Step Functions, Notes, and Video 5. A step function is a function with a graph that is a series of horizontal line segments. Because each part of a step function is linear, this is called a piecewise linear function. So pieces of linear functions. One example of a step function is the greatest integer function, written as f of x equals the greatest integer of x, where f of x is the greatest integer not greater than x. For example, 6.8. If I'm looking for the greatest integer function of 6.8, that means I need the greatest integer that is not equal to that. So 6. I'm almost going backwards. I'm not rounding up. I'm going to the greatest integer that's not greater than x, so 6. Because 6 is the greatest integer that is not greater than 6.8. So again, our ideas of knowing what integers are really come into play here. Positive and negative whole numbers, and 0. Graph the following parent function. State the type of graph, domain, range, and end behavior. So we're looking for the step function of x. So I'm going to start by making my table of values, just so I can see the idea of the greatest integer function in practice. So I'm going to pick some values for x, and I want some of them to be decimal, so I'm going to go with some easy ones. Let's do 0, 0.5, 1, 1.5, 2, and 2.5. I could also put some negatives in there too, but I'm going to start with these. So now, what is the output for those? So I need the greatest integer of 0 is 0. The greatest integer of 0.5 that is not equal to x would be 0. The greatest integer of 1 is 1. The greatest integer of 1.5 is 1. The greatest integer of 2 is 2. The greatest integer of 2.5, but not equal to x, is, or not greater than x, is 2. I'm going to plot those points. Right, so I'm starting with the kind of the easy ones. I'm saying the whole numbers. Right now, so this is made up of segments of lines. So right now I just have dots, and I only graphed these nice easy ones. So now let's do the other ones. So 0.5 and 0. Well, 0.5 and 0 would be somewhere around here, but remember it's all decimals, not just this one that I found. So I'm going to show a line, but the output cannot equal the x value. It cannot be greater than the x value, so I'm going to put an open circle there for not included. Same thing here. I'm going to continue my line, but an open circle for not included. So now I have a bunch of linear functions or pieces of linear functions. Now I'm going to continue this and continue the pattern. Both up and down the graph. Remember, open circles from greater than, less than are not included, not inclusive. And there is our parent function for a step function. All right, so what type of graph is this? Well, we know it's a piecewise function, but we really don't know what that means. So let's just say disjointed, because they're not joined together. Segments, or line segments. Okay, what is the domain? Well, it looks like this is going on forever, so our domain is all real values, or all real numbers. So I'm going to use the symbol for all reals. The range, let's see, if we go over here, we're just talking about the y, the outputs here. It looks like they're all whole numbers, but they can also be negatives. So again, we're going to use, that's any integers. And our end behavior, as x increases, y increases. And as x decreases, y decreases. All right, we're going to do b together as well. Graph the following functions. State the transformations that have been applied to the parent function y equals the step function of x. All right, I'm going to start again and make a table of values. I'm going to do it a little bit slower this time. Kind of show it in a couple different ways here. So I have my input, my output, and my rule, just to help me get a handle on this. So I'm going to pick some more values for x, and again, I want some decimals, so let's do 0, let's do 0.25, no, let's not, let's do 0.5, 1, 1.5, 2, 2.5. So if I'm just going to talk about what's inside that step function, and do x plus 2. So I get 2, 2.5, 3, 3.5, 4, and 4.5. And then I want to take the greatest integer that's not equal to x for my output there. So I get 2. I would get 2. I would get 2. I would get 3. I would get 3. I would get 4, and I would get 4. So again, all of these values cannot exceed these values. Okay, and then I'll graph it. And that's what your function should look like. So the next piece is to talk about any transformations that may have occurred. So it looks like if I look at my parent function from above, I started at the origin, and I'm no longer at the origin, I'm actually way over here. So it looks like when I have something inside the step function notation, within the parent, within the x there, it looks as though I'm shifting 2 units, and it's 2 units to the left. Just like, again, when we did with our absolute values, when we did with our quadratic functions. So I'm shifting 2 units to the left. Or translated, 2 units left. All right, I'd like you to take a moment and do C on your own. When you finish, press play. Make sure again for C you talk about the transformations that have changed. Maybe you can even make an assumption right now before you start what that negative out front means and what that positive 3 at the end means. Once you finish, just reset replay. The notation that one often sees for the greatest integer function is f of x equals this notation. Karl Gauss, a German mathematician, first introduced the greatest integer function in the early 1800s. Later, Kenneth Iverson, a Canadian mathematician, defined the floor, interesting floor, the greatest integer function, and the ceiling functions, and introduced this new notation in 1962 as seen below. Both notations are used in mathematics. These functions are used in computer programming languages, among other applications. So, floor looks like this. Notice that the symbols we were using before, it's not a good one, is a bracket kind of with a line inside. And now it looks like on the floor, we have the bottom brackets. And the ceiling, we have now these upper brackets. So that's how we know the floor, the brackets are on the bottom, and the ceiling, they're on the top. So kind of a shortcut for memory there. All right, so the floor of a real number x, denoted by the floor of x, is the largest integer not greater than x. Okay, opposite almost then. The ceiling of a real number x, denoted by the ceiling of x, is the smallest integer not less than x. So smallest integer not less than x, or largest integer not greater than x. All right, on the back page, we're going to do a couple together. Letter A, graph the following ceiling and floor functions. So first, letter A is a ceiling function as denoted by the notation there. Alright, so I'm going to again start with my x and y values. Alright, so I'm going to start with some nice easy numbers, so 0, 1, and 2. And then I need some decimals, because again, the ceiling and the floor functions talk about the greatest whole value, or the least whole value, or integer. So let's just do 0.5, and 1.5, and 2.5. Alright, so 0 is a whole value, so my output will just be 0. 1 is a whole value, my output would be 0, and the same with 2. Okay, so now for a ceiling function, again notated by these up here, means we need the smallest integer not less than x. Okay, so the smallest integer not less than 0.5 is 1. The smallest integer not less than 1.5 is 2, and the smallest integer not less than 2.5 is 3. Now I'm going to plot those points. Again, I'm going to start with the easy ones first. So I need 0, 0. Let's use a different color. 1, 1, and 2, 2. Okay, now I need the points where x is 0.5 and the y value is 1. So 0.5 is here and up 1 is here. Since I'm talking about all the integers that are less than that, but not including the smaller one. So it means my open circle is going to be in the lower half of all of these steps. And we could continue to go the whole time. And we're done A. I'd like you to do B and C on your own, and we'll come together and do a floor one. So let's do D together. Again, I'm going to start with my table of values. All right, and since I have multiple things happening within within the step function, I'm going to use 3 columns to make it easier. Again, I'm going to start with some easy numbers and then work towards maybe getting some decimals. So let's do -2, -1, 0, 1, 2, and see if that's enough. So I'm going to do 1/2 times -2, 1/2 times -1, ½ times 0, 1/2 times 1, and 1/2 times 2. Alright, so I'm just going to get some results here. So 1/2 times -2 is -1, and that's an integer. 0 times 1/2 is 0, which is an integer, and 1/2 times 2 is 1, which is an integer. So I really need to worry about these decimals here. So I'm looking for the floor function, and a floor again means the largest integer not greater than what's within the bound here, within the step function. So I'm going to do the easier one first. I'm going to do the positive. 1/2 times 1 is 1/2. So I need an integer that is not greater than x. So 1/2, the greatest integer that is not greater than that would be 0. The largest integer, not greater. The largest integer that is not greater than 0. Next one. So I have 1/2 times -1, which is -1/2. Okay, so now the two integers that wrap around that would be 0 and -1. Okay, so now I need the greatest integer that's not greater than that. So the greatest integer that is not bigger than -1/2. Well, 0 is bigger than what -1/2, so I'd get -1. Let's see if we can plot these points. So I'm starting with -2, -1. I need 0, 0, and I need 2, 1. Okay, now let's try to find out we're doing the ceiling, so I have, hopefully you have an idea of where we need to have the open versus the closed circle, but let's keep looking. So negative 1, 1, or sorry, negative 1, negative 1 is right here. So then we have 1, 0. So that looks like our pattern is we're going to start with the solid dot and end with the open dot. And that makes this a ceiling, I'm sorry, a floor function. We'll just continue. All right, so now just check again. The ceiling function starts with open, ends closed, and the floor starts with closed, ends open. I'd like you to do B and C on your own, and we're going to do E together. I think you could handle it on your own, but it's the first word problem, so we're just going to do it together. Letter E, cell phone companies charge by the minute, not by the second. So if I talk for 3 minutes, it's one price. If I talk for 3 minutes and 59 seconds, it's a whole new price, because they're charging per minute, not per second. A cell phone company charges Joe 45 cents per minute, or any fraction thereof. So once he goes over 1 minute and 1 second, it's now he owes 90 cents for exceeding the number of minutes allotted on his plan. The graph below represents this relationship. All right, so then our questions, and if we look at this, do we think this is a floor or ceiling based on how this graph is made out? Since we start with the open circle, it's a ceiling function. How much will Joe be charged if he goes over 7.5 minutes? So 7.5 minutes would be somewhere in here. So since we have an open circle at the bottom, or at the beginning, it means we have a ceiling function. If he goes over 7 minutes, he's not charged for 7 minutes, he's charged for the next full minute, or the 8th minute, which again is here. So he's being charged that 8th minute, so $3.60. Okay, what if Joe spends 3 minutes and 2 seconds? Okay, so 3 minutes and 2 seconds would be somewhere there. So we go back up here. Again, he's not paying the price for $3. He's actually being pulled up, paying the price for $4, which is $1.80. Next one, 9 minutes. So we're going to take 9 and go all the way up. So 9 minutes. As long as he doesn't go over, he's charged $4.05. All right, last one. Joe paid $2.70 in overage charges last month. Write an inequality that represents the range of possible minutes Joe went over last month. So if he paid an additional $2.70, we need to find where that is. Looks like it's in this range here. So let's see. Let's say that X is the number of minutes. He had to have spoken on the phone for less than 6 minutes and greater than 5 minutes. Now, if he speaks for equal to 5, he would only be charged $2.25. So X has to be greater than 5. Now, if he speaks for exactly 6 minutes, he would still be charged $2.70. So we need or equal to. All right, I'll go back and finish the problems that you haven't finished. And again, keep track of any questions that you have so we can go over those and they're fresh in your mind for in class. Good luck.